everyone. I've muted you all just because we had 118 as of this morning. So we're going to do a Q&A a little bit later. So yeah, this is really exciting. So okay, so welcome to the STORK Summer Series. So we are the Society for Transparency, Openness, Replication in Kinesiology. Very young, new society. So this is super exciting that Kristen was able to gather or unite, over 100 people to focus on the principles of effective statistics. So the reason for this particular summer series is many of us in this room probably were supposed to be in San Francisco, which I'm near San Francisco, but we were actually supposed to be at a conference, ACSM, where we have usually a meet and greet, which wasn't going to happen. So we pivoted and decided to do a meeting, which then turned into a series of meetings, discussions, and journal clubs. So please consider joining us as we move through the summer. And so I think we're going to just get straight into it.
Sure.
And so we have, Kristen Sainani from Stanford University. She's in the Department of Epidemiology and Population Health, which is very appropriate during our current, why we're on Zoom. And she's going to discuss principles of effective stats. And so please, as we go through the talk, just put questions in the chat box, and we'll do a Q&A at the end. All right, Kristen.
Great, thanks, Vanessa. So happy to be here today, and going to talk today about principles of effective statistics. And I like this particular quote. It says, "Statistics was developed to root out," I can't see things here on my screen, to appraise evidence, quantify uncertainty, and generally to keep us from fooling ourselves. Increasingly often, it is used instead to aid and abet weak science, a role it can perform well when used mechanically or ritually. And I think, unfortunately, all too often, statistics is used in a ritualistic or cookbook or black box fashion. And it's too often taught that way as well. It looks something like this. You kind of stick your data into the black box of the computer, click a few buttons, and out comes some results. And the problem is, if you don't really understand what's going on inside the statistical black box, and you don't really understand what the results mean, it's very easy to fool yourself. And when I was making these slides, I thought it would be fun to draw a picture of a mock statistics cookbook. But then I went to Google and I found that there are actual statistics cookbooks out there for real. So this is an actual statistics textbook, and it is not satire. It says, "Your statistics cookbook, easy to follow recipes for the most common statistical tests. Makes doing a 2-sample t-test for the difference in dependent means as easy as baking chocolate chip cookies." I found that one pretty funny. And then I also found Machine Learning in Medicine, cookbooks 1 through 3, and the Excel Data and Statistics cookbook. And to be fair, I have not opened any of these textbooks. It might be that they are perfectly wonderful textbooks inside, but the fact that we have books named statistics cookbooks does show you that this approach is all too common. And it's not unique to biomedicine. And so I found this in an archaeology text, actually. It says the main reason the cookbook approaches to statistics have been popular, especially in the field of archaeology, is that they offer comfort to those who are insecure about their own abilities to do quantitative analysis. And I think he's hit upon something really important there. I think the reason that a lot of people resort to cookbook approaches to statistics is because they are not confident in their own ability to do statistics. And when you are intimidated by statistics, you tend to check your common sense at the door. So if we are going to improve the quality of statistics in the literature, one of the things we really need to do is to help applied researchers have more confidence in their own ability to do statistics. And so I like to teach these 7 principles of effective statistics. These are things that I think are absolutely essential to getting your statistics right and to doing a good data analysis. You'll notice, though, that most of the things on this list do not involve, you don't have to be a mathematical genius, you don't have to have years of training in math and statistics. Most of the things are pretty straightforward. So like the first thing up there, checking and understanding your data. That is, for me, about 90% of a data analysis is just cleaning and processing data. It's super important because if you don't do that right, then it doesn't matter how good your fancy statistical model is, you know, it's garbage in, garbage out. But of course, that doesn't require you doing any math. And then when you get your results out of your computer, you have to step back and say to yourself, what do these numbers mean? Like, do they make sense? Are they plausible? Are they even possible? And again, that doesn't require a huge amount of training in math or statistics. 2 and 7 up there do require a little bit more training. So I do think it's critical that you document all your steps in code. That does require that you know some amount of coding, but that will help you to avoid errors and also to catch errors or to be able to trace back errors when they do occur. And it's also essential for reproducible research. And then of course 7, unpacking the black box. That takes some further training in statistics. Presumably that's all, you know, why you guys are all here is to start unpacking the black box. But I think, you know, a lot of the approaches to statistical teaching to date have kind of assumed like, oh, applied researchers are just incapable of unpacking that black box. And I think that's a complete mistake. Of course, applied researchers can unpack the black box if given the right tools and if taught statistics well. So if we're going to improve the quality of statistics in the literature, one of the things we have to do is to help applied researchers to unpack the black box. And they're perfectly capable of it. So what I'm going to do today is I'm going to give some examples that illustrate the importance of each of these principles of effective statistics. And I'm just going to start here with checking and understanding your data and keeping an accurate record in code. So I'll start with a story here. I had a medical student a few years ago who was working on a paper on sun protection habits in runners, something that interests me. And he had prepared a paper, was ready to send it out actually for review, but decided to ask me to check it before he sent it out for review. So I'm reading along in the paper, and I get to this sentence in the abstract. Women, older runners, and runners with a history of skin cancer were less likely to report consistent use of sun protection. And I thought, that doesn't really seem right, because I happen to know that women and older people tend to be more conscientious. And also you'd expect that people who had had skin cancer would be more cautious about sun protection. So I immediately suspected that there might be a 1-0 reversal error. And this is actually a common error that can happen. So what I thought might have happened is in some of the, he was running logistic regression. In some of the computer programs, you can accidentally model the probability of 0 rather than the probability of 1 without realizing it. So I thought that's maybe what went wrong. We checked his logistic regression code, it was just fine. So then I said, well, can you send me the code that you use to clean and process the data? So unfortunately, he hadn't done that in code. He had done his data processing within Excel, which makes it a lot harder to trace back errors. But luckily, it wasn't a huge Excel file, so I was able to go through and to trace back the error. And so what happened is that use of sun protection while running had been coded on this Likert scale, where 1 meant always uses sun protection and 5 meant never uses sun protection. He wanted to do logistic regression, so he wanted to collapse that into a binary variable. And he wanted to make always and frequently equal to consistent protection equal 1. But unfortunately, when he was recoding, he just assumed that 4 and 5 meant, the good behavior. And so he recoded 4 and 5 as consistent protection equals 1, and 1, 2, and 3 as consistent protection equals 0. You can see that that's an easy mistake to make. Luckily, we caught this before it went out for review, before it was published. But I wonder how often these types of mistakes actually go unnoticed. And these are the kinds of errors that worry me a lot more than, the subtle choices in your fancy statistical model. If you make this error, you're going to get exactly the wrong answer because everything is going to be backwards. So this kind of error really, really worries me. This is why it's so important to properly clean and check your data and keep a record in code. Now, I happen to be working on at the moment a data analysis, and I thought it might be useful for me to just kind of share my data checking and understanding process, because this is what I've been working on and off for like the last 3 or 4 weeks. So I have data, it's a 7-year longitudinal study of collegiate runners. The outcome here is bone stress injuries. They recently completed data collection. It was truncated just a slight bit early because of COVID. And I have been, for the last 3 or 4 weeks, preparing the data for analysis. That's all I've done so far. I have not built any models. I haven't tested any hypotheses. I am just focused on getting my data cleaned up. And what that entails is a lot of me emailing back and forth with the people at the various sites who are in charge of the data and saying, hey, can you check this person's value in REDCap? It looks like something might be off. Can you go back to the medical records and fill in this missing data? I'm probably the most annoying person to them at this moment. And I just thought I'll just show you. I have lots and lots of pages of code written so far. So here's what my code looks like. It's not a very well cleaned up code. I apologize for the messy code, but this is just me getting things down and cleaning the data. And so I do a lot of coding in SAS. So this is SAS code. And the first 3 pages of my code so far is just notes to myself. And these are a lot of notes like I actually went in and changed some data points in REDCap myself. And that's because there were some errors that were very obvious what the error was. But I didn't want to make a change to the data in REDCap without documenting that. So I documented all that. And then I'm doing like things like calculating new variables from old variables or renaming variables. So like gender was named sex in REDCap. And I don't know if one means it's a binary variable. I don't know if the one means male or one means female. So I recoded that as is male to remind myself what 1 and 0 mean. There's really important data points that every athlete needs to have. So I need to know exactly when every athlete was enrolled in the study and then exactly when every athlete was disenrolled from the study. Some of the athletes were missing that data. So I have to go to the people who are entering the data in REDCap and say, you got to go back to the records, find that data and enter it. It's longitudinal data, so I'm doing a ton of things with dates. I'm calculating the amount of time each athlete participated in the study. I am calculating how much time they lost due to bone stress injuries. Just a lot of changing variable names to make them easier to type. That's really critical. It's a huge data set, hundreds of variables. I'm paring it down to just those I'm going to need for this analysis. I'm merging the data set with other data. So for example, I have some data on vitamin D that I processed with separate code. So I'm going to merge that back. I'm preparing different forms of the data for analysis. So there's just a lot of steps that go into this. This is, again, for me, about 90% of the data analysis is cleaning and processing the data. And then what I'm going to probably be doing over the next few weeks is just taking every one of my variables and looking at it to see, what every variable looks like. Distribution, summary statistics. Do I have values that don't make sense? This is really, really important because if you get this wrong, then if your data have problems in them, it doesn't matter how good your statistical model is, you could end up with results that are wrong. So it's really important to do. You can see it's a bit tedious, but I actually kind of enjoy data processing and cleaning. It's a little bit zen, I think. It's kind of like when you go into the back of your closet after 5 or so years and you organize and clean out the back of your closet. It feels pretty good. You feel like, you've accomplished something. I kind of feel like data cleaning is the same. So here's all the things I'm going to be doing over the next few weeks. I will do all of this before I ever test a hypothesis or build a statistical model. By the time I go to do those things, I really understand the variables in my data set. And just for the purposes of this lecture, I haven't gotten to these steps, but I thought it would be fun to pop the performance data into a histogram, just because you're all sports scientists and you'll appreciate performance data. Now, performance for this study is not a main outcome. This is just a secondary variable. I actually haven't cleaned this variable yet. We had middle distance to distance runners, so 800 meters to 10,000 meters. And so the way performance was measured was we used a conversion formula to convert everybody to a 1,500 meter equivalent time, just so there was one metric you could kind of compare across. When I was making this slide, I put these, the women's and the men's performance times into histograms, and I immediately saw that there were some problems. And so, for example, I have 3 women who are under 4 minutes for their 1,500 meter equivalent time. Well, the world record for women is 3:50. So I thought, that doesn't seem right. So I actually checked, and we did have a data entry error, and the conversion formula was actually applied incorrectly in 2 cases. And then same with the men. There was a 3:18 1,500 meter equivalent time, which would be a world record. So that's obviously not, something's wrong there. And so I went back and got that fixed as well. And so you can see, like, errors are really, really common. This is not atypical. There's going to be some errors in your data. You need to go and clean them. The other thing I'm going to do when I'm just getting to understand the variables in my data set is I'll throw all of my variables into a big correlation matrix. Now, I'm not going to be reporting these correlations in my paper. I don't care about what the p-values are here. all I'm trying to do is get a sense of like what variables in my data set go together. So like I just threw in, I've got a variable that's the total number of fractures that a woman had during the study. This is, I've collapsed the longitudinal data just for the purposes of being able to scan across the variables quickly. And I wanted to see like what things correlate most strongly with your fracture, the number of fractures you have. And it turns out bone density is the thing that's most strongly correlated. If you have weaker bones, you got more fractures. Totally makes sense, but that's good for me to know. And then cumulative time in the study, how long you were followed. If you were followed for longer, you had more fractures on average. Well, that totally makes sense too. Of course, if you're followed for 4 years instead of 2 years, you have more time to fracture. So all of these things make sense, but they're really important for me to keep in the back of my mind when I'm analyzing the data, because I'm going to have to account for the time at risk very carefully, for example. So this is all that happens, you know, before you test a hypothesis or build a model. It's really important because you need to understand your variables before you do any of those further steps. All right, so that's data checking. The next example is going to illustrate the importance of paying attention to simple numbers and using common sense. So this is a figure from a paper, and this was sent to me by a colleague a few weeks back. This is a figure from a meta-analysis, and so each of the dots on that graph represents a study. And what the meta-analysis was looking at is they wanted to see whether or not if you improve your squatting ability, does that improve your sprinting times? And these were soccer players. So these were all studies in which soccer players underwent an intervention. And before and after the intervention, sprint times and squat power was measured. And they wanted to see if those two things were correlated. And when they did a Pearson's correlation coefficient, which corresponds to the scatter plot you see here, they found a correlation of negative 0.77. You want it to be negative because negative numbers in sprinting are good. That means you got faster. So they concluded the present meta-analysis suggests that there is a transfer of lower body strength training to sprint performance, as indicated by the very large correlation between squat strength, effect size, and sprint effect size. Now, the reason my colleague has sent me this particular graph is that she was concerned about one data point. She flagged what she called a rogue data point. I think that's a good description of it. So there's a study that's kind of far away from the other studies. And the effect that a data point that's far away from that cloud of points on the bottom, the effect that can have is that that data point can pull the line towards it. That can cause a seriously high correlation coefficient. And that's indeed what's happening here. If you took away that one data point, actually the correlation is much, much weaker. We started to dig into this a little bit more though, and to ask the question, well, what does that data point even mean? So you got to look at the x-axis here. We have sprint effect size, and on the y-axis, it's squat effect size. And then we've got some numbers. Well, what do those numbers signify? What does -5 mean? What does +3 mean? So these are effect sizes measured as standardized mean differences. So the authors took the mean, like sprinting ability or squatting ability after the intervention, subtracted the mean before the intervention, divided by the pooled standard deviation. They're pooling the before and after standard deviation. So the units for effect size here is standard deviation units. So if we look at this rogue data point, it has a y value, a squatting effect size of almost 15, an improvement of almost 15 standard deviations in squatting ability. And for sprinting, it was an improvement of almost 5 standard deviations in sprinting ability. Again, negative is good here. You want to get faster, so you want your times to go down. Kind of step back when you get results like that and ask yourself the question, what do those numbers mean? And are they possible? Are they plausible numbers? And in fact, if you start to think about it, you realize that an improvement of 15 standard deviations, that's a little bit unbelievable, actually. And so I actually went and pulled the paper that corresponds to that rogue data point, and just to see what does a 15 standard deviation improvement mean in the context of this paper. And so those soccer players were squatting an average of 123 kilograms at baseline. The standard deviation at baseline was around 8, I'm rounding here. A 15 standard deviation improvement over the course of the intervention would mean that they went up by 15 times 8. That is a 120 kilogram improvement on average in squatting ability. And so this, to me, although I don't know much about squats, seems like an implausible and probably impossible effect size, because this is just on average, meaning that some athletes would have had to improve even more than that. And so indeed, this actually is an impossible effect size because an error was made here. And I wonder if anybody wants to take a stab at guessing what might have gone wrong here. Feel free to type into your chat box. Think about, this is a meta-analysis, right? So, oh, somebody said pounds versus kilograms. Good guess, but that could do it. Yep. Different denominator in the effect size calculator. Yes, good. Thank you, Erin. So yes, they've put the wrong denominator into the effect size. So think about when you're doing a meta-analysis, what you have to extract from the original papers. So you've got to extract the means before and after, and also the standard deviations before and after. So think about what you might extract that sounds like a standard deviation, but actually isn't, and that you might erroneously put in as the denominator of your effect size, right? And so what it turns out to be is they indeed have the wrong denominator of their effect size. So in some of the original papers, authors didn't report means and standard deviations in their tables. They reported means and standard errors of the means. It's a common thing you see. And you can see how it would be easy, though, to accidentally extract those standard errors if you weren't paying attention to, you didn't read the title of the tables. So what they happened is they extracted standard errors rather than standard deviations. Well, that's a big difference. And those standard errors ended up in the effect size calculations. And so what that means is their effect sizes end up being much too big because their denominators are too small. And so squatting ability improved on average by about 25 kilograms. The standard error was around 1.7. So that translates to an effect size of 15. But of course, what goes in the denominator here is the standard deviation. And so if you correctly put the standard deviation in the denominator, the effect size is actually about 3 standard deviations. Still very big, but not impossible. And same for sprinting ability. The standard error was 0.02. Standard deviation is 0.09. So the correct effect size here was actually about -1. And you can see that this is the kind of error that could happen very easily. You know, you're doing a meta-analysis, you probably have some students extracting that data for you. And the student goes to the paper, they extract the mean plus or minus something. They don't pay attention to the fact that there's a difference between standard error and standard deviation, or they don't notice that standard error is reported. That ends up in the database, you calculate some effect sizes. It's totally understandable how an error like that would crop in. But at the point at which you've got results, that's where you need to stand back and say, okay, let me just do a gut check test and make sure those results make sense. And hopefully that's the point at which this kind of error should be caught. All right, so the next example illustrates the importance of drawing lots of pictures, graphing your data, and considering the totality of the evidence. So this example comes from a randomized trial of a supplement for knee osteoarthritis. All the patients have knee osteoarthritis. They're given either a supplement or a placebo. And the authors of this paper actually did not graph their data. They just put it in a table, but I graphed their data for them. I just took it out of the tables and I made these 2 graphics. These are the 2 primary outcomes, pain and disease severity. And you want both of those to go down. Lower is better. This was a 24-week study, so the athletes were, these are not athletes, patients were measured at 4 weeks, 12 weeks, and 24 weeks. So on the x-axis here, we have time in weeks. And on the y-axis, we have the percent change since baseline. And I put the outcome in percent change since baseline because it just makes it a little easier to compare treatment and placebo here. So treatment is in blue, placebo is in red. And I don't think it takes a degree in mathematics to be able to interpret these graphics correctly. So again, if you have, if you want to, I'm curious if you want to type into your chat box what you think, how would you interpret the results of this study? Do you think the treatment, there's evidence here that the treatment is effective? Anybody want to take a stab at it? I think, you know, I'm hoping we all arrive at the same answer, but if anybody wants to type in their take on these data, you know, does anybody think that the treatment did better than the placebo? Remember, lower is better. All right, so yeah, clearly no effect. Somebody typed in, thank you. So yes, there's no effect, right? I mean, we don't see any evidence that the treatment is more effective than placebo here. If you look at the pain, actually, if anything, the placebo group is slightly better than the treatment group. Of course, that's not a significant difference, but you know, it seems like clearly the treatment group did not beat the placebo group. On osteoarthritis severity, they take kind of different paths, but they end up in the same place. So this seems pretty easy for us all to agree that there's no evidence here that the treatment is effective. It might surprise you then to read the abstract of that paper. So here is the abstract of that paper. The authors conclude, these results suggest that consumption of the supplement has a positive effect on osteoarthritis score. In contrast, it does not reduce pain. So they got the pain part right. But how is it that they are looking at their data and concluding that there is a positive effect on osteoarthritis score? Well, part of what happened here is that they didn't graph their data, so they didn't realize that this was the pattern in the data. And what happened here is they applied a repeated measures ANOVA to their data, which is a perfectly valid test for these data. And they looked at the group by time p-value, which is actually the correct p-value to look at. But they found a significant group by time p-value. Unfortunately, a significant p-value doesn't mean treatment beat placebo. When you get a significant p-value, you have to look at the context of that. So why the repeated measures ANOVA gets a significant p-value here is simply the fact that both treatments follow different trajectories over time to get to the same place. So like treatment went up and then down and then across, placebo went down and then up and then down. That will actually trigger a significant group by time p-value, but that doesn't mean that treatment beat placebo. That's why it's so important to graph your data. And then if you actually keep reading in the abstract of this paper, it's interesting because they then say these results show that consumption of the supplement has a positive effect on self-reported knee function, and also self-reported knee function, by the way, that's the osteoarthritis severity score that we just looked at. But then they also highlight that it had a positive effect on household physical activity. So where did that come from? Well, it turns out that they are highlighting sort of a cherry-picked result out of their data. So if we look at table 2, which is a rather cluttered table, we see here's all of the data from their study. They had 2 primary outcomes that we already talked about, but then they also had 4 secondary outcomes. They looked at leisure time physical activity, household physical activity, timed up and go, and 6-minute walk. And they looked at 3 time points, 4 weeks, 12 weeks, and 24 weeks. And they used that to calculate 18 different effect sizes. They calculated Cohen's d, standardized mean differences. And if you look just at household physical activity at 24 weeks, it kind of has a largish effect size of 0.8, and it's statistically significant. So if you look only at that one effect size, it looks interesting. But of course, you have to interpret that one effect size in the context of all the other effect sizes. And if you kind of scan your eye down this list here, you notice that a lot of the effect sizes are negative. That would mean the placebo actually did better than the treatment. And so I just took all of those effect sizes from the table and I plotted them in a histogram to show you what the distribution of the effect sizes looks like. If you look at it, what you have is negative again means placebo did better. So we have half of the effect sizes, the placebo did better than the treatment, and in the other half it was positive and treatment did better than placebo. And it follows this nice, beautiful, normal distribution. Well, this is exactly what you expect to see for the distribution if the treatment is completely ineffective. You expect to see a bit of a normal distribution with a few effect sizes out in the tail, and it's centered right around 0. Exactly what we would expect to see if the treatment has no effect. Household physical activity is that little point at the end, the 0.8 there. This is a household physical activity at 24 weeks. You know, that could be real, but it's exactly what I would expect to see if this was just a chance finding. I'm expecting to see this distribution with a few things in the tail. So when I see this and look at it in context, it says to me, I really don't have any evidence that the treatment is effective. This looks like a good null result to me. Yet if you cherry pick that one result off the end, then you can spin a story that this treatment is effective. All right, the final thing I want to talk about today is unpacking the black box. And if you're going to be doing your own data analysis, I do think it's really important that you unpack the black box. And you have to have confidence in your own ability to do that. You're all capable of unpacking this black box. This does require some further training. So you do need to learn some basic concepts in statistics and probability. And then the other thing I highly recommend that you invest some time learning is something called computer simulation. I'm going to focus today on computer simulation because it's one of the most powerful and important tools in statistics today. So first of all, computer simulation, again, it's just this immensely powerful tool. And even in the last 20 years, computing power has increased just an amazing amount and has really made it possible to do very large computer simulations in very little time. This wasn't true when I did my dissertation, slightly back in the dark ages. So when I was reading my dissertation, one of the chapters was I was comparing some estimators for something called two-stage sampling. And as part of that, I had to run simulations. And so I think I was running these simulations with maybe 1,000 repeats, which is actually a really small simulation. I used to have to put my simulation running at the end of the day. When I left the office, I left the computer running the simulation. I would have to come back in the next morning. Usually took about 12 to 15 hours to run these simulations. And then I would get the results of my simulation. It was really annoying if I went back in the next morning and the simulation had not run correctly, because then I had to do the whole thing over. I can now take that same simulation, I can pop it into my laptop, and I can run it in less than a second. So that's how much computing power has advanced even over the last 20 years. This means that a lot of things are now possible to do on a computer. Now, I know that computer simulation, when you say that, it sounds really intimidating. It sounds like it's a really hard thing to do. But actually, you gotta believe me that it's actually relatively easy compared to the math. So I've been teaching for a lot of years now, and I do encounter a lot of students who struggle with math, who are really phobic of math. They tend to find computer simulation very intuitive and very doable, even if they don't like the math. So I think it's actually really intuitive to do computer simulation. I teach this in my first, my introductory stats course to students who have never programmed before. It's great because you can solve problems that are not mathematically tractable, that you actually can't solve mathematically. I sometimes will actually use computer simulation to help me solve tough math problems. So the way that I solve math problems is I cheat and I run a computer simulation, I figure out the answer, and then I work backwards to the math solution. Computer simulation can give you an intuitive feel for actually how statistics behave. Statistics have behavior, and you want to understand when they work well and when they don't. You can understand that with a computer simulation. So if somebody asked me to evaluate some kind of newfangled statistics, which actually I was doing last weekend because I was reviewing a paper where somebody proposed a new statistic, or if I'm going to use a model that I've never used before, first thing I'm going to do is I'm going to pop that into a computer. I'm going to simulate some data where I know what's going on in the data, and then I am going to run that statistic on those data to get a sense of how that statistic behaves in the real world. That helps me build confidence in my ability to use that statistic well. So this really can help you build confidence and unpack the black box. So I just want to give a quick example that illustrates how computer simulation even works. And I'm going to use a simple problem that probably a lot of you have seen before, because you probably all had a Stats 101 course. And this is a classic probability problem from Stats 101. So it goes like this. It says, in a classroom of, say, 30 students, what's the probability that at least 2 will share a birthday? And I mean the same day, not necessarily the same year. So 2 people born on February 5th. When you ask people this question, and if they haven't seen the problem before, they tend to think it's a really low probability, 5 to 10%. But it turns out to be surprisingly high. Actually, it's about 70% probability for a classroom of 30, which is a little counterintuitive. You can solve this problem mathematically. So here's the mathematical solution. It involves combinations and permutations. It's super fun. But again, not everybody likes math. And so when I teach my intro stats course, I don't focus on the mathematical solution. What I do is I focus on having my students write a simulation to solve this problem. So let me walk you through how the simulation works. So in the simulation, what you have the computer do is you have the computer randomly generate 30 birthdays from the possible set of 365 birthdays. And I'm skipping leap year, sorry if you were born on February 29th. And what you can imagine the computer is doing is sort of imagine that you've got a 365-sided die. And I couldn't find a picture of one, but you can imagine what that would look like. And you have the computer roll that die 30 times and come out with 30 numbers. Those numbers, the numbers 1 through 365, represent birthdays. So 1 is January 1st, 365 is December 31st. So then you get a virtual classroom with 30 virtual students and 30 birthdays. And then you can check, did I get a match? Did 2 numbers match? You then do this a large number of times. So say do this 10,000 times, so that you can then calculate in what % of virtual classrooms did I get a match? Well, that's the probability of getting a match. And it matches the math solution. And just to show you, not to scare you with code here, but the amount of code involved in this is actually really small. It's just one little loop, and you're doing some sampling, and then you're checking to see if there's a match. Most of my intro stat students have no programming experience coming in. They can write a little simulation like this a few weeks into the course. So I know it looks intimidating, but it's really not bad. And I just want to unpack this a little bit more. So I went into R and like grabbed out the first 5 virtual classrooms that R generated. So here's the first 30 birthdays. And in the first classroom, I actually got a match on the 251st day of the year, which is September 8th. And in the second classroom, I got a match of 45 and 45. 45th day of the year, that's Valentine's Day, so 2 people born on Valentine's Day. Third and fourth classrooms, no match. The last classroom, I actually got 2 matches, 2 born on the 16th and 2 born on the 134th day of the year. Now, out of this little tiny set, it's a 60% hit rate. But of course, that's not a very reliable number. We have to do this a large number of times. So I did this 10,000 times, and about 70% of the classrooms have matches. That matches the mathematical solution here, to a certain point, to a certain decimal place. If I want to match to more decimal places, I'm going to run this simulation more times, maybe 100,000 or 1,000,000 times. You can do this 1,000,000 times on your computer, no problem. The great thing about the simulation is there's more you can do with it, though. You're not stuck here. You can then say, like, let me answer a more difficult problem. What if I ask you, what's the probability that 3 students share a birthday? That problem is actually really hard to solve mathematically, but it's like super simple to change your simulation to look for 3 instead of 2 matching. Or if you want to build in something like, right now we're assuming that all birthdays are equally likely. What if you wanted to build in that like more people are born in July? You can easily build that into the simulation, much harder to do with math. So there's a lot of power at your fingertips with a simulation. So the last example I wanted to present today, I wanted to show you how computer simulation can be used to help unpack the black box of statistics when you're doing your own data analysis. And I'm going to use an example from sports science. So I was recently working on a systematic review of over 200 sports science papers with some of my colleagues. And as part of that review, we had to read the statistical methods sections of each one of these papers. And it kept jumping out at us. We saw like the same language almost repeated, almost verbatim, across many different papers by many different authors. And it struck us that, what was probably happening here is that all of these authors maybe were using the same statistics cookbook to do their statistics, and that's why it was the same language, like almost cut and paste across all these different papers. And one sentence in particular that kept jumping out at us is the sentence you see here, and it kept jumping out at us because it was using unusual terminology to describe a common statistical concept. So because the wording was unique, we kept noticing it. And so the sentence was, all variables were log transformed to reduce bias because of non-uniformity of error. And we saw this in lots of papers. I'm just showing you 4 examples here. Now, non-uniformity of error, I think what they're talking about there is what we commonly call non-homogeneity of variances. The homogeneity of variances assumption, as probably we've all heard of, is something that underlies linear models. So when you're doing t-test, ANOVA, or linear regression, this is something you're supposed to check. But what struck us when we were reading these papers is that it was just this sentence over and over again. And it wasn't, the authors didn't say, we tested our data for non-uniformity of error or non-homogeneity of variances, and we found that the assumption was violated, and therefore we log transformed, and then we checked the log transform data to make sure that it didn't violate the assumption. There didn't seem to be a lot of thought going on here. Really, it just seemed that there was an instruction in the cookbook that said, do this, and then cut and paste this reason into your paper. And that's really not a great way to do statistics. This is where you've got to have confidence in your own ability to unpack the black box. So don't trust when somebody says to just do this because of this reason. Try to understand why, and try to understand why you're doing that. And so this is a really good example of where you can use a computer simulation to help unpack a black box. The black box that we're going to unpack here is this homogeneity of variances assumption, which underlies linear models. So you ought to ask the question, like, why does it matter? Why am I checking this? Or, transforming all my variables because of it? And when does it matter? That's really important. When does this assumption actually matter? So we can use a computer simulation to help us get a feel for the behavior of this assumption. And so what I did was to set up a computer simulation. And now I'll tell you that this simulation is slightly more complicated than the birthday one that I just showed you, but it's still actually not a really hard simulation to run. My intro stats students can run a simulation like this by the end of the term. It's not a ton of code. It's actually not terribly hard to set up. But what I did is I'm setting up a simple case where I'm comparing two groups on some type of continuous outcome. So imagine I'm comparing two groups, treatment and control, on say like VO2 max. And I'm going to measure VO2 max just for simplicity on a standard deviation scale. So I'm going to randomly generate 60 VO2 max values for the treatment group using a normal distribution with a mean of 0 and a standard deviation of 1. That's just your standard normal curve, and it can give me a bunch of continuous values for the treatment group. And then I'm going to randomly generate 60 values from the same normal distribution for the control group. What this does is it gives me a scenario where there's no difference between the treatment and control group. They have the same exact means. So I know that the null hypothesis is true here. I'm also setting it up such that my variances in the two groups are equal. And so I'm starting with a scenario where you're going to meet the homogeneity of variances assumption. I take those simulated data and then I just stick them in a t-test. And specifically, I have to use a pooled variance t-test here because the homogeneity of variances specifically applies when you're using a t-test with a pooled variance. So I run a t-test and I'm going to get out a p-value, and I am going to focus on the p-value because what happens if you violate this assumption is that your inferences are off. You get the wrong p-value. So I need to look at the distribution of the p-values to see if they're behaving correctly. So I start with my assumption where I've got equal sample sizes and I've got equal variances in the two groups. And here's what results from that simulation. I'm going to get, oops, I'm missing the actual base simulation disappeared here. So I'm just going to go 2 slides ahead and show you this is exactly what this simulation looks like. So when you start with the base simulation and you have equal variances in the group, so 60 per group and a variance of 1 in both groups, what you get when you generate those 100,000 p-values is a uniform distribution. So your p-values, this is a histogram of the p-values. The x-axis here is 0. It's equally likely when the null hypothesis is true, which is the case here, that you're going to get p-values anywhere from 0 to 1. It's evenly distributed across 0 to 1. This is exactly what you expect to happen when p-values are behaving well and the null hypothesis is true. So this is what we want to see, this uniform distribution. What this means is that 5% of the time you're going to get p-values between 0 and 0.05. So if you use a cutoff for statistical significance of 5%, then you will have a type 1 error rate of 5%. 5% of the time you're going to get significant results. You're going to erroneously conclude that the groups differ when they in fact don't. So this is the graph that we want to see. And this is the graph that I get when I have equal variances in my two groups. But I then varied the simulation, and the one I'm showing you here, because for some reason it disappeared off the other slide, and this is the case actually where I made the variances different in the two groups. So I made the control group have a variance of 3 times the size of the treatment group. Notice though that the behavior of my p-value is still perfectly fine. My p-values are behaving perfectly here. So even though I violated homogeneity of variances, it's actually absolutely no problem. My p-values are just fine. This is the graph we want to see. Now you might say, well, okay, but maybe you haven't made the variances unequal enough. Maybe you got to make them more unequal. So then I went and changed this to a variance of 10 in the control group and a variance of 1 in the treatment group. Way different, very, very unequal variances. But notice that my graph is still just fine. My p-values are behaving exactly as they should. So I still have a type 1 error rate of 5%. I'm still uniformly distributed. This is what we want to see. So everything is fine. I'm violating homogeneity of variances, but it's actually no problem at all for the index. Now you might say, well, okay, but you've got a really big sample here for a sports science study. 60 per group's larger than most sports science studies we see. So what if you had a much smaller group? What if you had a really small study, like 10 per group? Then what happens if you have uneven variances? So if you have 10 per group, if you have a really small study, here's the results of that simulation. It still looks perfectly fine. Now, if you're looking very, very carefully, you'll notice the type 1 error rate budges up just a teeny bit. It's 5.2% now instead of 5%, but hardly makes a difference. So I've got unequal variances, very small sample sizes, and I'm still pretty much just fine on the inference. I then am going to make one more little tweak to my simulation, though. I'm then going to make the sample sizes of the groups unequal. So what I did next was to change my sample size in the treatment group to 90 and my sample size in the control group to 30. My control group, my smaller group, has the larger variance. I've got unequal variances, unequal sample sizes. And now if you look at the distribution of the p-values, now there is something wrong. It is no longer following a uniform distribution the way it should. We have too many small p-values in this case. So actually now the type 1 error rate suddenly goes up to 13%. 13% of the time, even though there's no difference between the groups, you're going to get a significant p-value at a significance level of 5%, 0.05. So now there's a problem. This is when the homogeneity of variances assumption matters, when you have unequal sample sizes. And you can show mathematically why this is the case. I want to make sure I leave time for questions here at the end, so I'm not going to go into the mathematical details, but you can show that what happens here in this scenario is that you end up underestimating the standard error. Well, if you underestimate the standard error, you're going to make your p-values too small. You're going to end up with too many small p-values. You're going to have a high type 1 error. Now, interestingly, if I swap this such that the larger variance goes with the bigger group and the smaller variance goes with the smaller group, then you get a totally different pattern. Still not a good pattern. This is still my p-values behaving badly, but it's kind of the opposite pattern. Now your p-values are actually too big, so you end up with a lower type 1 error rate of just 1.2%. This, of course, is not great because you're now going to inadvertently increase your type 2 error. And again, mathematically, you can show why this occurs. In this scenario, you end up overestimating your standard errors, which means that your p-values are going to be too big. And you can show this, you can go further in the simulation, you can kind of show this behavior systematically. I'm not going to go 3 days just because I want to leave time for questions, but I'm just showing you systematically that, that this basic conclusion holds. The homogeneity of variances assumption is very robust as long as your group sizes are equal. Where it really matters is when your group sizes are unequal. So this means that, do you need to log transform all your variables because of this? No, clearly not. In fact, even if the homogeneity of variances assumption is unmet and you have unequal sample sizes, another way to handle that is just to use a t-test with an unpooled variance. So there's other ways to handle it. This is why it's important to really unpack that black box and understand why this assumption matters and when it matters. And I think I will wrap up there to leave time for questions, but I'll just point out a few further resources for your own learning. I write a statistics column for the journal PM&R, and the link is there if you want to go and check out those columns. I do a lot of specific topics, some more basic, some more advanced. So if you want to learn a little bit more about p-values or principal components analysis, logistic regression, I have a lot of columns there. And then in February, recently, I launched a medical statistics certificate program through the Stanford Center for Professional Development. That is a 3-course series. I am not assuming any prior programming experience. I will teach you to code in either R or SAS. And I will also show you in the second part of that, in the second course of that, how to do these kinds of computer simulations. And I think I will stop there and make sure that we have time for questions. So you can go ahead and type your questions into the chat box. I like the comment about using Fortran with shoe boxes full of punch cards. That was luckily before my time. I'm not that old. Oh, and thanks, Aaron typed in, for those interested in simulation, the FAUX package in R will be helpful, and he's put a link in there for that. And so anyway, you guys can go ahead and type in your questions, and happy to chat more. All right, so I am getting a question. To what extent do you think cookbook approaches are useful for different audiences? For instance, I'm thinking about those choose your statistical test flowcharts. Do we build from those approaches in undergraduate statistics into something more nuanced, or does this require more of a paradigm shift in statistical education from the bottom up? So I'm going to answer both, yes to both of those questions. So I actually think those statistical flowcharts can be helpful. So what I notice a lot of my students do when they take my courses, they draw one of those flowcharts for themselves. So those kinds of frameworks can be super helpful. I have no problem with you drawing a flowchart and having a framework, as long as you unpack each of the pieces of that framework, right? So I think those are useful tools, and I'm not against those kinds of tools. Does it require a paradigm shift in statistical education from the bottom up? Absolutely. So if you have one of those flowcharts and that's all you're teaching the student, and then you show them the buttons you press to hit each of those nodes, then that's absolutely not a good way to teach statistics. So I think it does require a paradigm shift, and I'm hoping that that these kinds of talks that we have can help people to make that paradigm shift. And part of that paradigm shift is, I think, believing that applied researchers are actually capable of unpacking the black box, and not just assuming like, oh, they're not going to be able to do that, so we're just going to show them how to click the button. Another question, is there a rule for using standard deviation and standard error? So standard deviation and standard error are totally different concepts. And one of the most fundamental concepts that you should learn is what is standard error and what is standard deviation. This is one of the things that on qualifying exams in my department, you're going to see a question from me about what's standard deviation and what's standard error. And so standard deviation tells you something about the variability of the traits that you are looking at. So that's what that concept means. Standard error tells you about the variability of the statistics that you are looking at. So standard error is a special case of standard deviation when you're talking about variability of statistics. This is a hard concept for a lot of people to get their head around, because what does it mean for a statistic to have variability? You do one study, you get one mean. How does the mean have variability? Well, it turns out this is a theoretical concept. So this is where a computer simulation is great, because what a standard error is, it says if you could repeat the study over and over again, what's the distribution of the mean or whatever statistic you're looking at? What is that going to look like? You can do that with a computer simulation, or you can do that with math. And so standard error is actually telling you something about the variability of your statistic. You use standard error when you're making inferences. That is when you are talking about calculating a p-value or making a confidence interval. But you use standard deviation when you want to say something about the variability of the trait, such as to calculate standardized effect size. Another question, do you see any issue in getting a colleague trained in statistics to do your stats and just try to understand the basics of what was done? Or should we strive to understand all our analyses inside out? Okay, so the optimist in me says we should all strive to understand all our analyses inside and out. So if you are doing your own data analysis and you're the primary person doing the data analysis, I think the onus is on you to understand what you're doing. That is, if you're just clicking some buttons and putting things into a black box, that's not a great process. There's lots of situations though where you might work with a statistician. So like I'm working on this data analysis now, but I'm not the PI on the study. The PI on the study is the person who put together the study, collected all the data. I'm just coming in as a statistician to analyze the data. And so this is a situation where one option you have is if you're not confident in your own ability or you haven't had much training, is to work with a statistician to analyze your data. That's the ideal situation, of course. But we don't all have the budgets to hire a statistician. So sometimes I realize you're analyzing your own data, but if you're going to be analyzing your own data, you better understand enough about what you're doing. So we should all strive to understand all of our analyses inside and out. I realize that that's a high bar, but boy, that would improve a lot of the quality of the statistics in the literature. Okay, if you had to offer a top piece of advice to improve sports science research, aside from increasing sample sizes, yes, that would be one, what would that be? Would you focus on improving statistical applications and inferences, or would there be something more fundamental regarding study design and implementation? Oh, that's a great question. It's going to be hard for me to pick one. I mean, I think you need to improve statistics along the entire pipeline. So that means starting at study design. So maybe like the advice I would give is see if you can engage with a statistician from the beginning of your study. When you're designing the study, get some input from a statistician to make sure that you are designing the study correctly. Because unfortunately, if that step goes wrong, like if you don't sample enough participants, it's really hard to rescue the data later. But equally important is the data cleaning step, and equally important is the data analysis step. So I don't think any one of those is more important than the others. They're all critical. And so understanding all of those is super important. Somebody writes, don't use magnitude-based inference. Yes, as some of you probably know, yeah, I would say that is an important piece of advice. I'm not even sure that's the top piece of advice, but that's a good start because that's an example of cookbook statistics and certainly can lead you astray. I've got a question, missing values. I guess mean imputation is generally a bad practice. Is interpolation okay, or should we always aim for a full analysis without using imputed values? Okay, so yeah, so the problem with mean imputation, if you just like give everybody the mean value, what's going to happen is that you're going to shrink the variance of that variable. So you imagine if you fill in 10% of your or 20% of your data points in a variable with the same value, your standard deviation is going to be too small. So that's why mean imputation isn't ideal. Now, let's say you have a variable where you're missing 1% of your sample. If you use mean imputation, is it going to be a problem? No. you're, 1% isn't going to greatly shrink the standard deviation. So if it's a few data points, that's totally fine. Go with the simple. If you've got a lot of missing data, a lot of high percentage of your variables missing, 10% or more, then you probably want to use some kind of multiple imputation routine that is a bit more complex. It does require some more programming. Should you always aim for a full analysis without using imputed values? That's the ideal. So that's why I'm spending so much time now, like going back to the people who entered the data on my data set that I'm working on now, to say, can we fill in any of this missing data? Because the best thing is to just have no missing data. I realize that's not always feasible. So you do the best you can. Another question, most exercise or sports science statistics analysis is not pre-registered, so most can be labeled as exploratory. What would be your guidance be in interpreting exploratory analysis versus confirmatory analysis? So that's a great question. Yeah, I mean, most of the studies are not pre-registered. Some that are not pre-registered will still have been designed correctly and have a primary hypothesis, and I think can be correctly interpreted as confirmatory. But from what I've seen in the sports science literature, I would say that that's right, that a lot of the research is actually exploratory but mislabeled as confirmatory, or written in a way that implies that it's confirmatory. So there is, something to be said for exploratory research, as long as you are crystal clear in your write-up that this is exploratory and that it's not saying the treatment works because it's based on exploratory research. And let's see. And thank you, Erin, for pointing out that we have a paper giving some alternatives to MBI that's on a preprint with Daniel Atkins. And what's one measure you look at to understand the severity of COVID-19? Of course, we had to have a COVID-19 question. Couldn't escape it. I thought I was going to get away with one lecture without a COVID-19 reference. Yeah, that's a complex question. So the epidemiology of COVID-19 and calculating things like the case fatality rate, it's super complicated. What's one measure we would look at? I think there's a lot of things you could look at for COVID-19. Some of the most interesting data to me actually is the data where they're showing what's the normal mortality rate overall across all causes in different countries at this time of the year. You can look at averages from past years, and what you'll see is there's this huge spike. So some of those we don't know if those are due to COVID, but it's a good indication that that really big spike, that COVID is doing something different than in earlier. So I actually find those pretty convincing. I've got a question. Does moving to Bayesian analysis solve some of the sample size issues in sports? Not in my mind. So I'm all for exploring different types of approaches to statistics. I've actually seen in my reviewing of papers, there's I've seen several papers now that have used Bayesian analysis. I think it's great to, for people to be aware of all these other approaches. But the idea that if you switch from a p-value to a Bayesian analysis, you're going to improve all of your statistics is just purely false. These are two tools. P-values, frequentist statistics, that's a tool. Bayesian statistics, it's a tool. Those tools can be applied wrongly. So if everybody, doesn't unpack the black box and just switches to doing Bayesian analysis from a black box, nothing is going to improve. And you still need to get decent sample sizes, even if you're in a Bayesian framework. And I think if you're going to do a study, may not be worth doing if you've got 5 people. Let's see, I know I'm running a little long, so Vanessa or Jennifer, you can stop me if we need to wrap up. What are your thoughts on determination of smallest effect size of interest in sports science? Most work in the field uses what could be best considered as proxy outcomes, but are captured because they are easier to capture than actual sports performance. Do you think specific research programs looking at determination of smallest effect sizes of interest for these proxy measures anchored to actual sports performance or a worthwhile pursuit? Yes. Yeah, so the behavior in the systematic review that we did, that we saw that a lot of people were using for their standardized effect size of interest, just blindly using 0.2 standard deviations. That's not a good idea. That may or may not have any real meaning anchored in the real world. So even if you're using proxy measures, you have to think carefully, if you're going to use a minimal effect size of interest, how to choose that. And it takes work. There is work involved in that, but that is certainly a worthwhile pursuit. Yeah, absolutely. And you discussed effect sizes a few times today. Is there an effect size statistic similar to the partial eta squared, but for linear mixed models? Well, so for linear mixed models, I'm going to look at the beta coefficients. So it's just like looking at beta coefficients from a regression. Good. Okay, so I'm aware that we've run about 5 minutes over. Thanks everyone for bearing with me. And I will let Vanessa wrap it up. Thanks.
Kristen, thank you so much. I think, am I unmuted? Hopefully.
Yes.
That was awesome. All the chats were great. There's going to be a recording of this, and all the links, I will send out an email with everything in to everybody that was in the session. And just thank you so much. This was great.
Sure, happy